Yeah. Hi, I'm Subhadra. My teammates Dilip and Anirudh, and I will be presenting our work on Scalable Big Data Analytics with Dask. So this is our agenda where we'll be discussing about the problem statement, why we chose this problem, then why Dask and XGBoost for the benchmarking. Then we'll explain about the setup, then the challenges that we faced, and the conclusion. Data is getting generated every moment, every day, and it has continuously been growing. So working with huge amount of data and doing the analysis is a big task. So we use traditional tools like pandas, scipy, etc. for analysis. But most of the time we get kernel issues and memory errors. So here we introduce using Dask integrated with XGBoost. Why Dask? It is a versatile parallel computing framework that seamlessly scales Python data analysis tools while offering the real-time monitoring. So yeah. Here we choose XGBoost for scalability and Optina for integration for accurate hyperparameter tuning, which is ideal for distributed ML tasks with a vast hyperparameter grid. So we have implemented Dask integration with XGBoost, which can be seen in the following code. So in the code, Dask distributes the mentioned objective function in parallel for different workers, and their output is stored inside the Dask storage. Then, after every iteration, the optimization function checks which parameter is to be optimized.
Right. So for the proposed task for this project, so we're initially going to create a Dask cluster and then deploy it on AWS. And then to perform a benchmark study, we will run an XGBoost algorithm for our data, and then we're going to use Optina for hyperparameter tuning. And by varying different configuration of your cluster, that is your workers, your threads, your input data format, we will perform a detailed study and then compare the benchmarks metrics.
Let's now move on to the cluster setup. To begin with, the architecture of our cluster has four different aspects: the Jupyter server, the scheduler, the client, and the workers. The Jupyter server is a front end for the user to run code and submit jobs to the cluster. The scheduler receives the code from the Jupyter server and then divides the work between the 6 worker nodes. Building our setup involves 5 major steps. We will look at these one by one in detail and finally connect to the notebook and the scheduler and see what it actually looks like in action. Before we create our cluster, one crucial step to do is create a key pair for the cluster. So under EC2, there is an option to create a key pair. So here we created a key pair called the Dask cluster key. This will be used in various setup wizards for our cluster. So next we move on to creating the ECS cluster. Here we specify the operating system as Amazon Linux 2, and then we provide the compute system as t2.micro, and we chose t2.micro because it was under the free tier eligible category, and we specify the number of nodes as 8. Next, in the same setup process, we also have to configure the network settings, but because we don't have anything specific to configure in our network settings, we just left these options and default and move on. So next we had to configure our inbound rules for the network. For this, what we do is we specify 4 different inbound rules. So first being the SSH access, and then we specify an access to the Jupyter notebook, and then we specify one for the Dask diagnostic page, and then we finally specify one inbound rule for the Dask scheduler to talk with all the worker nodes. So with the nodes up and running and the inbound rules defined, we need a persistent file system. So to do this, we make use of the EFS service in AWS, and here we created a storage for 30 GB, and we then mount this storage onto all our instances. But how we do that is we define a launch template. So for the launch template, we just specify few commands for the instances to run on startup. So the commands we specify are a few, such as updating all the packages in the instance, and then here we specify mount to the EFS storage drive, which is at this DNS address. So with the launch template created, we now need another tool to make use of the launch template upon the startup of these instances. So how do we do this? We make use of another tool called the auto-scaling group. So the auto-scaling group just requires you to specify the launch template and the number of instances that you want. So here I provided the Dask launch template, which I showed before, and I specified the number of instances as 8. So with this created, it will now automatically launch new instances with the Dask's launch template. So the launch template primarily is needed to mount the EFS system, but we have to make sure that it has successfully mounted. So to check if it mounted successfully or not, I went ahead and tried to SSH into one instance. So I took the IP address of one instance and then SSH'd into it using my Dask cluster key that I created in the beginning, and this logged me into the instance. Now that I'm into the instance, I then copied a few files into the EFS folder, and now that I've copied a few files in the EFS system, the next step is to check if all these files are also visible in the other instances. So then I went ahead and SSH'd into 2 more instances here, and then we can see the same files are shown everywhere, and you can see that the IP addresses are different, meaning these are different instances from the same cluster. So now that we have a cluster with a common storage system mounted successfully, the next step is to launch Docker containers into all of these. But to do this, I first built Docker images on my local system and then pushed them onto a repository in AWS. So now that I've pushed 3 different Docker images onto AWS, I now need another tool that can initialize these Docker images into containers in our instances. So for this purpose, I created a task definition. What the task definition does is it just takes the image, the Docker image, and creates as many containers as we want in as many nodes as we want. So I specified for the Dask notebook and Dask scheduler only one node for each of them, and then for the Dask worker I specified 6 nodes, so that adds up to 8 nodes in total. Here we can see the definition for the task definition I was talking about. Here I specify the link to the repository of our Docker image, and then I'm just specifying the container port that needs to be mapped to the host port. So the containers port is already predefined in the Docker image, but the host port can be anything. This is so that we avoid any conflicts with um, a predefined port number. So for example, if 8786 was predefined already, then I would put something else here that will map to the container port 8786 so that it doesn't conflict with this port. But in our case, there is no need to create a new port ID because 8786 is not defined in the host already. So yeah, with this, you can see in Dask scheduler, I'm creating 2 port mappings. So now let's connect to the clusters. We will very quickly have a walkthrough of what the cluster looks like in action. So here I have my all the instances running already, and we can see there's 1 scheduler, 1 notebook, and 6 worker nodes, and that's totally 8 nodes. So if we need to connect to the instance and open our Jupyter server and run code, we'll have to go to the notebook first. So how we do this is first open the IPv4 DNS address in a new tab. So here I specify my IPv4 DNS address, and then I specify the port number of our notebook server. So that will be 8888. So here we are connected to the Jupyter server in our instance, and this requires a token ID. So generally when a Jupyter server is launched, the log files of the Jupyter server mentions the token ID for us to log into the notebook. So now if we have to find the token ID, we need to go to the log files of the Jupyter notebook. So how we do that is we go to the task definition of our notebook, go to the log files, and here we have the token ID. So we paste the token ID, and then this should open our Jupyter server. So with this open, now I need to open my scheduler as well. So let's open the scheduler. So let me go back and open the scheduler right here, copy the address, paste that here, and then 8787 will be the port number of the Dask's diagnostic page. So here we have the Dask diagnostic page. Now we need to also specify to the Jupyter server where our Dask scheduler is. So how we do that is, here we just mention the Dask scheduler's IP address, and then also specify the port number where the scheduler is. So 8786 will be the port number of the scheduler. So now let's try to run some code and look at it in action. So yeah, so I'm gonna very quickly run the code here. It's gonna show us that there's 6 worker nodes right here. So 6 worker nodes with all their IP addresses. I run this. Yep. then we can see that the the scheduler is passing the tasks to our worker nodes. So 1, 2, 3, 4, 5, 6, and that's exactly the number of worker nodes we have. So let's look at what the scheduler looks like actually behind the scenes. So the small glimpse that we're getting is how the Dask scheduler is dividing the tasks between the Dask workers. So with this, I hand it over to Dilip to show the XGBoost code and its implementation.
Yes. So now that we have finished with understanding how we set up the cluster and the XGBoost algorithm, etc., we will move to benchmarking and the kind of metrics that we use to perform this study. To begin with, we used CPU time as our first benchmark to understand how fast a piece of code ran. And then we used wall time that considers disk input and output, caching, and overall time that a piece of code takes. And finally, the accuracy measures that we obtained by varying the configuration of our Dask cluster. And when I say varying, the things that I varied was workers, that is the number of workers in the cluster, and the number of threads that each and every cluster had, and then changing the input data format from CSV to Parquet, etc. And then finally, to understand how parallelization happens in the backend of Dask, I used Task Graph to check if all these workers had computations running on it, etc. So the first observation. So the first observation is where we compare the CPU time and wall time of your normal XGBoost and your Dask XGBoost. So as you can see on the left-hand side, you see that the CPU time for your Dask XGBoost was only 5.44 seconds, whereas your vanilla XGBoost took over 23.1 seconds. Whereas for your wall time, the CPU time was 18.9 seconds and 25.1 seconds for your vanilla XGBoost. Now, the accuracy, even though there is not a lot of variation, you can see that single-threaded machine performed better when you compare to the accuracies that we obtain for dual-thread machines. Moving on, now to understand how much time it took for different types of configurations, namely one number of worker, 2, 4, and 6, and also comparing them with single-threaded and dual-threaded, you see that for dual-threaded machine, it took considerably less amount of time to optimize that particular XGBoost algorithm. At the same time, the wall time of dual-thread machines were considerably less when you compare to single-threaded machines. Now, to understand the different kinds of data that we used, so in the market, usually people use CSV, and when it comes to distributed data type, it is Parquet. So when you compare the amount of time Dask took for your pandas, you can see that Dask was considerably faster by at least, say, 500 times for both read CSV and for reading Parquet file. And on the right-hand side, what you have here is the task graph. When the number of worker nodes is increased from 6 to 8, you can see that there are a lot of white spaces, which means that at that point of time, the worker nodes did not have any form of computation, which means that the CPUs or the computation power was not being used efficiently. But when the worker nodes were only four, you can see that there are hardly any spaces for your computation. So which means that scaling up has to be done in a proper way. And also the code that you have should also be parallelized the right way to make efficient use of your clusters. And blindly scaling up does not impact your data or your analytics, etc. Right, results. So from all the project that we did in the past 3 to 4 months, the results that we obtained were a platform that is highly scalable, that could be used by a team member or an entire team to train machine learning models at scale or even perform big data analytics. And with that, we also performed a detailed study of task, then benchmarking with your traditional data science frameworks such as Pandas, Scikit-learn, XGBoost, NumPy, etc., to understand how much performance boost one can get by moving towards your distributed frameworks. And along with that, we understood how you can diagnose your parallelized code that runs on Dask so that you can efficiently use the resources of your cluster or even your local uh, working machine. All right, the challenges that we faced. The first challenge was to understand how we can have the same kind of dependencies on all the worker nodes, your client, your scheduler, because once we had finished setting up the entire platform, and then when we tried to run the code, we faced a lot of challenges to try and understand where the system was failing, only to realize that the same kind of Python version, the same kind of task, XGBoost, etc., had to be present on all the different worker nodes, client and scheduler, etc. And then parallelizing XGBoost code for data is slightly tougher when you compare to your normal implementation. So there's a slight learning curve present there, which took us some amount of time to understand. Learning outcomes. So in terms of learning outcomes, we understood a lot about task. Can we conclude that it is better than PySpark or Hadoop? To a certain extent, in our view, I feel Dask is better for certain tasks. At the same time, your PySpark and Hadoop is definitely better for certain tasks. And we learned about AWS, your Docker, the IAM roles present in AWS, especially when we created a root account and then we all wanted to work together in different roles. And then this was our first benchmark studies. So picking the right metrics to actually show the comparison was important to us. And then error logging and making sense of the error logs is or was a very fundamental thing that we learned, mainly because to understand where the entire setup was crashing, we had to go back to our error logs, check, then make changes, and then again run it, go back, check, etc. We also learned about how you can parallelize your day-to-day machine learning algorithms such as XGBoost, and I also learned how you can parallelize other machine learning algorithms such as your linear regression, logistic regression, etc. And as a team, we learned how to coordinate with each other. That is similar to how computation is distributed over your clusters. We distributed our tasks based on individual interests. Moving to future work, definitely I would want to benchmark with data that is greater than 50 GB. So because of resource and time constraint, we have performed benchmarks only on data that is 800 to 1.2 GB. And then I would want to perform a detailed analysis on Dask, PySpark, and Ray, which are our modern distributed frameworks, and would definitely look forward into understanding more about Ray, which from what I've researched about is better in terms of every aspect compared to Dask and PySpark. And programmatic deployment of Dask cluster on AWS and building bigger cluster because we are mainly dependent on the AWS UI for all this, but we would want to do it using the AWS CLI and then have the cluster up and running in as much less time as possible. Conclusion. So we had an amazing learning curve in terms of understanding what engineering cloud computing was, how to create Docker image containers, deployment on AWS, and then what Dask is, what parallelization is, how you can efficiently write code to parallelize your task by decreasing the amount of computation time. And then we had amazing time working together within the team, distributing work, and then understanding each and everyone's individual interest and strengths. And now that we have finished the entire project and then we've started with our final report, we are looking forward to finalizing it and then submitting it on 26th. And lastly, we would like to thank Juliet and Xian and Tian for their wonderful feedback, especially after our initial project proposal. So we used that feedback to narrow down our project, and then we kind of had great time coming up with different project ideas. And then finally, we have a project ready. So thank you, everyone.